All right. Hello, everyone. My name is Farzad YousefZadeh. I want to thank our great MC who introduced me already, and I want to use this stage as a chance to say a big thank you to all the organizers of HolyJS and you guys for being here to make this happen. If you want to follow me on Twitter, well, you should. I'll be usually talking about the same topic over and over, and I usually spend more time on Twitter rather than my own work. So you can just follow my activity there. But besides joking, I will publish the materials for this talk right after the talk on Twitter. I'm a senior software engineer, recently joined Epic Games. People ask me to do Fortnite dance on a stage, but I really can't because I have never played Fortnite. I used to come from an academic background back in the college by studying aerospace engineering and a bit of astrophysics. I've always been a nerd in high school, observing the night sky and reading mathematics and physics. But then something clicked on my mind on the last semester of college, so I dropped out of college because I thought I need to pursue something else. So I'm a self-taught software developer with a bit of experience for almost 6 to 7 years. So to give you a general glance of what we're going to talk about today, the talk is going to have different scenes. I try to make it as tangible as possible because the topic is not, despite the thing that the MC said, it's not about UX. It's related to UX, but it's more or less about modeling and state management for client apps. And we're going to talk about the state throughout the whole talk. So we were going to talk about implicit versus explicit states. What's the meaning of these two, and what are the differences? And what does it mean when we say finite and infinite state? And what benefits do we get out of separating these two types? So then we're going to move on and talk about logic, how we can model it, how we can visualize it, and how we can use it in a way that's decoupled from the implementation and use it as a way to port the logic throughout different platforms and use it as a means of communication in the team. So scene of the talk will be about the what. I'm going to describe what we're going to talk about today. The topic is a very old industry topic with almost as old as 3 decades and has been heavily used in embedded programming and programming for mission-critical programs such as elevators or avionics systems like the aircraft UI, something that like sort of systems that people's lives are at the stakes. So that if you make a mistake, where if you get like undefined is not a function, the pilot will be gone. You lose the pilot. And the good thing about this topic is that I didn't invent it. No one else did invent it. It just happened over the time in the history of computer science. And it's quite challenging to learn it, especially for people like me who don't come from computer science background. Because when you search them and you look them up in Google, you will definitely go to Wikipedia, which will describe them as quintuple. So I tried my best to make it as tangible as possible with practical examples and case studies, and we have 2 live codings. So please bear with me. Have you seen this statement before? The premise that says UI is a function of a state. If you have ever used a modern framework or library that gives you the ability to build your UI upon composing different components over each other, and having components and whatever, this premise comes as a tagline, like React, Vue, the new Angular. They're all working based on this premise. And it basically talks about the fact that you can just take care of the state, and you can declaratively declare and define what you want to render, and how it's going to be rendered and implemented down to the platform level is going to be abstracted away by the platform. But today, our focus will be on the purple part, which is the state. In JavaScript, we have different ways to do one thing. We are dealing with different state management tools. For example, if you wanted to update one property called title in your store or storage or whatever you want to call it, then you have different ways based on the tooling you choose. If you go with domain-specific solutions, such as React props and state model or React hooks, or you go with like Vue's internal reactivity or whatever, you can just update whatever you have, like perform a mutation based on how it works internally. And you can also use some other global shared state-based solutions, such as Redux, MobX, and do the same thing. Some of them use observable, some of them use decorators, some of them just use unidirectional flux-based architectures. But in my opinion, state management tools that we use these days are not managers. They're containers. Why? Because they're more or less are handling a layer, and they're trying to solve a layer of problem that is dealing with the architecture. It's more or less talking about the mechanics behind how you distribute your state throughout the course of your application. It can be based on a Flux architecture like Redux, or it can be following a push-based mechanism or a pull-based mechanism. Either you subscribe and ask for, you subscribe and the store will tell you that there is an update, so you re-render, or you will just try to do short polling and ask for changes whenever there is a change there. They also deal with how you store the state. They give you a way to either use a single source of truth, like Redux, or distribute it throughout different sources, like what MobX and MobX State Tree do. In addition to that, they also give you a way to tell how to update the state based on how they internally handle it as implementation detail. It can be mutable, it can be immutable, it can even be subscribing to a certain observable. But what we're going to talk about today is quite different from those levels. On the left side of this slide, you can see that normally when you deal with the state management tooling, you have actions, reducers, store, and whatever is related to that tool, and you have a view. You subscribe, or they subscribe, or however it's handled, then you dispatch an action. And that's how the flow is going on. But today, we're going to try to add a modeling layer in between. We want to decouple the modeling and the logic from the implementation itself, and we want to talk to this modeling layer by sending different events from the view, and then how you batch, distribute, or collocate, or whatever you want to do it on the modeling layer, and the modeling layer will talk to the state management tool if you even have a need for using that state management tool in your application. But before getting that, let's have a quick flashback to the graphical user interface histories. By looking at the history of GUI, we can see that the first traces of using event-driven architecture to manage an event-based system like UI has been started from the process of research and development that Alan Kay and his team were doing back in 1972 to be able to make an interactive UI for a portable computer that was carrying the purpose for educational, for kids. So it was supposed to be a portable notepad, for instance, that children, was as easy and interactive for a kid to be able to interact with it and learn something. And surprisingly, they came up with a model and implemented something in the research phase, not the implementation phase, of course, it was 40 years ago, that it could handle most of the complex interactivities we see in almost 2020 in UIs, which was amazing. And there are some evidences that they were using Smalltalk as the main language for that research and implementation. So according to this phrase in the GUI history, the first traces of using event-driven architecture to manage complexities and modeling in UI goes back to 1972 in Smalltalk. Those days that the first drafts of object-oriented programming were coming out by Alan Kay and his team. So it's still almost 2020, and we're still using event-based architecture. Amazing, right? Or problematic? Well, it's your judgment. In an event-based architecture, you would follow a paradigm called event-action paradigm. What does it mean to say event-action paradigm? It means the way we deal with UI, and we try to talk to it and make some changes to re-render those changes for the end user, is that we'll listen to events, and we map those linearly, probably one-to-one, to side effects I want to execute. But let's see what are the shortcomings of following these paradigms even after more than 40 years. To state the problem here, I want you to look at a video, which describes it far better than me. It's about the bot for FaceTime.
Her phone raised. Okay, her phone raised. Add a person. Finna call myself. And her phone answers. Hello.
Bro, what the?
So let's get back, because that's on autoplay, and that's not like loop. I don't want to play it again. The problem with FaceTime was that it was carrying a severe security bug. And that means you could eavesdrop and listen to someone, regardless of them being accepting the call or not in FaceTime. You could call someone, even without them actually accepting the call. You could just add some people, bring on some UI, try to add someone, and it would establish an audio connection with someone who hasn't even accepted the call yet. So you could listen to people. That was a security problem. That was obviously a violation of privacy.
Self-caller.
We will see what the problem is. For the second example in the history, we can take a look at the experiment at Ian Horrocks, or I'm really sorry if I'm pronouncing the name wrong, Mr. Horrocks. So he's the author of a great book called Constructing User Interfaces with the Statecharts. And back in 1992, he talks about an experiment in this book where he has spent almost 10 minutes with the first prototypes of Microsoft Calculator program that was shipped with Windows. And he managed to produce a lot of runtime logical errors. Why did that happen? Because OK, before that, let's say what happened. He was trying to click on the minus button, the button that was labeled with a minus, and the button that was labeled with C, which is supposed to clear some sequences. And what he managed to do was that he managed to reproduce a couple of runtime errors. And why that happened? Because this application has been developed by a UI builder that was working based on Visual Basic. I forgot the name for some reason. So it was based on the output of a GUI builder based on Visual Basic, and you could probably just create a layout, drag and drop some buttons, put a label on them, and say that when the user presses this button, do this. But the problem is the connection between the events and the side effects we execute in UI is not always linearly one-to-one mapping. Sometimes we want to do conditional logic. For instance, the minus button, depending on the context that it was used in, it could have done two things. One of them was that if it was being used in a sequence of numbers, then it would have subtracted two consecutive numbers in that sequence. But if it was being used before the first number in the sequence, it should have negated that number. So it converted -2 to +2 and vice versa. So the event handler for this case needed to know about the context it was being used in. And also, these event handlers, since they wanted to be aware of the context, it means that you needed to turn your UI from a stateless pure function to your handlers from stateless pure function to something that was aware of the context, which we all know where tight coupling will end up. But to indicate what was actually wrong with those problems is that they were handling the states implicitly. They were trying to reason based on the input event and connecting that based on some conditions and execute some side effects. To understand the code base that handles states implicitly, like the code base on the right side, you have to understand the program. You have to go through the whole lines of code, trying to understand the first line to the last line to possibly understand what the logic is. This is not practical. Imagine this code base. Now imagine you're using it in an application like Instagram. You've had hundreds, millions, or even thousands of these, and you're supposed to understand all of them. And the code base is modular. You have to jump between codes. You have to jump between files. There's not always synchronous actions. There are asynchronous concurrent actions. How are we supposed to go through a code base like that and understand the underlying logic? To understand something that handles the state implicitly, you not only have to understand event handlers, but all the mutations, asynchronous side effects, concurrent side effects, and also other sort of side effects, like fire and forgets and promise-based ones. But those problems were old. Maybe we cannot relate to them. Let's have a case study on the sign-in form of Netflix. Let's see this video and see how the sign-in form, the inputs and the form are going to behave. When we load the sign-in form at first, we're going to see that both of the inputs are empty. There is no value. But we're not showing any invalid text, the orange text at the bottom of the input. Then you go on, you write something in the input, and then for some reason, now the validation error pops out. And then when you clear it, it's going to be remaining there. It just keeps it there. Unless you write something that is valid, and then it just removes that. Let's see how we model this using implicit states these days. So at the first iteration, the input is empty. There is no orange text, so we probably want to keep track of the value of the input, and we want to say if the value is false or not. We want to say if the input is valid or not. No value, input is invalid, but there is no error. The next step would be to write something there. So the value would be updated, but it's still invalid. So there is a value, it's invalid, now the validation error is shown. The third iteration would be to clear it out. Now the orange text is there, we still keep it there. So we get back to no value, again the valid Boolean is false. Spot the problem? The problem is we're trying to handle the state in a way and reason based on it in a way that one object might have different representation. Actually, the state that we have, and we model in this case, isn't even capable of modeling those representations in the view. So what we do, of course, we extend it with another Boolean flag. We go on and add another Boolean flag to say whether the input has been even validated before or not, so that we show the orange text conditionally. Now, the validated first is false because we haven't interacted with the input yet. Then validated gets true because we have validated and it's invalid. And then at last, when it's clear, we change it back to true. Actually, we keep it as true. And at last, when you write something valid, we keep track of the value again. We say it's valid, and we say that it has already been validated before. Don't use that. That's my personal email. I forgot to change that. But let's take a step back and think about reasoning in the state again. We're reasoning based on the length of the value of the input. We're reasoning based on variations of two Boolean flags, which are valid and is validated. So the first one, length is 0, valid is false, is validated is false. Second one, third one, and the fourth one. What happens here is that by taking another look at the table of the variations, we can see that the length of the value will have two different variations. The valid will have two different values, and the is validated will also have two different values. Have you seen the problem? Of course, 2 raised by the power of 3 different variations could be produced out of this state. But we only needed 4. So what happens to the rest of the 4? It's impossible state. So the variations where the length is 0 and valid is true and is validated can be toggled, and the two others will be something that we call impossible states. These are the states in the application that we didn't even want it to happen. We don't even want it to exist in the modeling layer. But we're modeling it in a way that the modeling allows it technically. So the code is technically fragile. The only blocker between the end user to break this and the actual breaking to happen is the UI that you disable the buttons in. So if something happens and the user can transition to these impossible states, that will be a part of bad modeling. And that's where the complexity of your code will actually allow more than the complexity of the problem you're trying to model. What happened? OK, yeah. So with impossible states, you will also need to write tests to avoid transitioning to these impossible states. Why? Because you might not be there in the project 2 months from now. You might leave the project. Someone else would be onboarded, and they would change something based on the new business constraints, and now, boom, the add person is FaceTime is now available. What happens there? The impossible state can happen now. So you need to write tests, not to make sure that the code works, but actually make sure that the code won't break. So the impossible state is the exact point where you tell the user to restart. Have you restarted Windows? It's because Windows transitions to an impossible state. Since the programmer didn't foresee and predict that, they didn't provide any way to recover. Have you interacted with the login form that the button is disabled, and the only way to write it from scratch, to submit the form, is to refresh the page and write from scratch? These are all different representations of impossible states in the wild. So, of course, not only for tests, but in the runtime, for avoiding transitioning to those impossible states, we add guards. And man, we add guards everywhere. You remember the code on the right side of this slide, a couple of slides ago? If you're writing Instagram or Facebook, if you're writing a complicated enough client application, you will have hundreds, thousands, and millions of these. And of course, if you write more guards, you're going to make it more consistent, but you're going to sacrifice. And what you're sacrificing is increasing the cyclomatic complexity of your code. The cyclomatic complexity is a term coming from probability and logical thinking, meaning that the cyclomatic complexity is a quantitative metric, a way to assign an integer to a code base as the complexity of that code base. Meaning that you can say, this code is as complex as 4, another code is as complex as 2. And what things increase the cyclomatic complexity? Things that you use in guards, things like if, else, while, for, switch, case. These are the things that branch. So they introduce another path for your code to end up with. So these are different independent paths that a program can take, and they increase cyclomatic complexity. So more guards means higher complexity and less predictable and understandable knowledge. But if you're already bored, I don't blame you. I got bored too. So we know that our program is not always as easy as using one single input that has a sync validation. We want to embed that in a form. Let's extend it to the whole login form. Let's say that there's also a password we don't care about, and we can reuse the implicit state for the input again, embed it in a parent object that is supposed to carry the implicit states of the form. So in order to indicate whether the form is being submitted or not, we carry a Boolean submitting. And in order to be able to represent the errors from the API, we keep track of the error. Let's go through the variations again. These are all the variations and iterations of the input again. They don't affect the form itself. But when the form gets submitted, we toggle the submitting Boolean. We still have undefined error, and when the response comes, if it is an error, then submitting gets turned to false again, and there is an error. So, of course, for implicitly handling the state of the form, we keep track of one Boolean and one error. And if the form is being edited, submitting is false, there is no error. If it's being submitted, submitting gets true, there is still no error. If it fails, then there is an error and submitting is false. And again, when it succeeds, there is no error and submitting is false. So the same problem that we encountered with the input, same modeling that should be extended again. And of course, it ends up in impossible states again. So we add another is success to extend that, and, well, same thing happens. So we not only add guards to avoid transitioning to the impossible states, but also we avoid going to mutual exclusivity problem. A mutual exclusivity means two things are not supposed to happen at the same time. So for instance, if the business logic says only the form can be submitted when all the inputs are valid, it means that form being submitted and form being validated are two mutual exclusive properties. They are not supposed to happen at the same time. But of course, with implicitly handling this state, as we saw before, we are technically allowing them. It's just a matter of dispatching the wrong action in the wrong time. So as front-end developers, what we do is that we disable the button. Pretty cool, right? Huge props to David Khurshid for this meme. But guess what? Disabling the button is not your business logic. Your code is not supposed to be fragile. Your UI shouldn't be the only way to avoid breaking your technical possibilities, your technical problems. Just you have to model the code in a way that is consistent enough. So imagine that you had a way you could model the code in a way that you didn't know whether it's going to be used as an iframe in another UI or on command line or on mobile or on web. You didn't care. The UI would have behaved in the same way, right? The platform, of course, it affects the behavior, but at some point, most of the behavior is abstract, and you can decouple it. So what's the solution? Going to the third part of the talk, I want you to think about the states from now on explicitly. Being able to explicitly think about the state means that being able to indicate the different behaviors of the UI you're building, put a fine line behind them, label them with a unique string, and calling them out. So we can say that, oh, OK, you know what? The form is in state A, then it goes to B, then it goes to C. And for that, you need to develop a skill to be able to discover those finite states. And that's the whole idea behind using finite state machines in practice. Finite state machines try to model the application in a way that is composed out of a finite amount of explicit states that you can call them with names, and then you can change between those states by transitioning based on events you receive. So in the input example again, the input, we can say that it's empty. That's the label we're looking for. We, of course, care about tracking the value of the input, but what we care about on a reason base is the empty string there. And then we say that this is invalid, there is a value. Of course, it can be invalid when there is no value, and we can say it's valid and there is a value. And again, you can see my personal email. So on the left side, being empty, invalid or valid, is called finite states of the single input, and the infinite state is the value you track, something that cannot be modeled as finite. Of course, you can also model that as finite state if you keep track of, if you have a state by the number of all the characters, symbols you support, and all the numbers. But that even blows more than the imperative code. So we have a notion of infinite states. We'll have live coding. Don't worry. And what we can do is that to transition the input between those states, we'll have to receive type. So that's when the user actually types in the input. Cool stuff. So if you want to somehow be able to draw the diagram of transition between these states, you can say that there are 3 circles for the states, and there are, of course, 6 arrows indicating the transitions, and the only event we support is type. And that's already quite complex for a single DOM input. And for using it in the runtime, you can use a union type to say that this input is either empty, invalid, or valid. And you can, for transitioning between that, you can write a pure function that uses a nested switch case based on the state and the event, and only reasons based on the final state and the event it receives and returns the newest state. So in the unchange of the input, you can change the value. And you can also always get the output of transition, which is a pure function, and put it as the next state of the input. And of course, you want to conditionally render to be able to show that damn orange text. So what you can do is that, again, have the unchange, and the only thing you need to conditionally render based on that and reason based on it is the invalid state. This is super explicit now. Everyone understands if input is invalid, render this. Whereas in the old code, you could have said, if it's not valid, and if it's already is validated. I don't get that. Going to the form, you can, of course, expand it as much as you can and say that the form is only valid and being able to submit and continue there if both of the inputs are valid. So when the form is valid already, both of the inputs can only be valid. Otherwise, inputs can be whatever they want. And the infinite state you take is the value for email, password, and the error that you possibly want to show if the submission fails. And conditional rendering, again, you can go on and disable this button, but if you don't disable, nothing will happen. Your UI is full of buttons that people will, by mistake, double-click. You hardly want to send a HTTP request again if someone, by mistake, double-clicked. And the only thing you want to show here is the infinite value that you track for the error. But once you get to you get used to thinking about finite states and explicit states, it's quite addictive. You would soon realize that finite states are everywhere in practically most of the interactive elements you use in day-to-day UI development. Any sort of popping out and popping in elements, such as tooltips, modals, popover, dropdowns, these always carry a finite state of opened or closed. Buttons are state machines. They have normal, hovered, active, active focus, and disabled states. And an input type of range or a slider, whatever you call it, and a progress bar can be either in the minimum value, a maximum value, or somewhere in between, and they will have a context for being able to say what the value is right now. But not only the elements, but also the side effects for using UI development can carry finite states and infinite states too. Promise, by definition, is a state machine. If you take a look at the table at the bottom of the slide, it's actually copy-pasted from the ECMAScript spec. So the underlying implementation of promise in your browser is actually a finite state machine. A promise can be either pending, fulfilled, or rejected, and it has a context for the value for resolve and reject. But what about the scaling? We, of course, cannot do this union type everywhere and try to nest all the state machines based on the complexity of our UI. So we need a better way. We need a way to be able to scale this and make it more practical. So we need a practical way to model, not only gets the states explicitly and separates finite and infinite, but also gives us a focus on the logic by abstracting all those implementations away and reduce the guards and all those conditional paths that we saw in cyclomatic complexity, and also is capable to model complicated graphical user interfaces. And that's what we call state charts. So state charts are an extension on top of the core value of final state machine by adding a couple of features to it to be able to extend it for complex user interfaces. It's originally coming from an academic paper published by David Harrell in 1987, once he was working, doing some research for the avionics system in Israel, where he talks about this, and he tries to model a stopwatch there, practically in the academic paper, and draw all the states of the state chart. It extends the basic core values of finite state machines. It gives relations to the state. Surprisingly, not all the states we see are flattened. Not states have structure, states have hierarchy, they have life cycle. They have to be disposed, they have to be cleaned up, they have to be initialized again. And they give you different places to run the side effects that you want with different support for different type of side effects. And they extend the idea of event action by adding a state for being aware of the context and the side effects, so going from purity to idempotence. But today, I'm just going to use XState, a library developed by David Khurshid, which is one of the implementations of state charts for JavaScript. There is also a lighter implementation. It's called Robot. But we're not going to use that today. We're just going to use the JSON-based definition of XState, which is based on SCXML standard. And it has a built-in visualizer, so I can actually show you the complexity of the things we're going to live code today. But for the finite state machines, for pure FSM, there are way more than enough implementations in JavaScript. But for state charts, XState, and Robot, as I mentioned. So let's rewrite our input in Netflix login form in state charts using XState. All right. OK, so what I'm going to do today is, OK, let's go here. You don't have to spoil everything. What I'm going to do here is that I'll use the basic template of Create React App, and I basically just install XState, and it's binding for React. I'll use React and XState, but feel free to use whatever you want. It's framework and language agnostic. You can just use it wherever you want. So I'll start the Yarn server. Yes, so this is a basic template. We'll go to the Netflix input directory. As you can see, the app.js is only the basic template of Create React App. There is no magic here. I've already installed XState, so I'll try to import whatever I want. We only need one factory from XState to be able to use the implementation of state charts, and we need a way to use this binding for React. So we use a hook, we feed it with a state chart, and it connects it to the React view. And we call it use machine. Cool. So let's see how the input was supposed to work. Based on this state diagram, we can see that there is 3 inputs and only one type event. We can basically transition between all of them. So let's see. So what we do is that we go on with a basic JSON definition. It's a declarative way, an abstract way to be able to be serialized, and we define the whole behavior and logic we want here, and then we will connect it to the implementation detail for XSA to pick it up from there. So what we can say is that state charts give you this notion to be able to say that every system starts from an initial state. We can call that empty because when we loaded the input for the first time, the input was empty, right? So we can define different states here. We can say the input has different states. It's either empty, valid, or invalid. And if it's empty, it receives a type event. And it will go to either valid or invalid. But being able to transition to multiple places based on one condition is something XSA gives you as an array of transitions. So we can define an array and say that when I receive type and I'm already empty, I can stay at empty, first of all, if Oh, come on, live coding. It was easier when I was rehearsing. So we can say that it will stay at empty if the input is still empty. We can give it a condition and say that if the input is empty, we'll feed the implementation later. I'll show you. And we can say that it goes to valid. Let's say it goes to valid first. If the input is invalid, and otherwise it goes to, actually, no, you know what? Let's go to valid if input is valid, otherwise go to invalid. And let's see if I have a, so I guess I have a predefined, oh yeah. Is that the one? No, I still have another one. Okay. Oh yeah, right. Where? And this one should, no, come on, that was right. And another one for empty. Yes, yeah, so we're done with live coding. So it just stays at empty, as we saw in this diagram, if the input is still empty. It goes to valid if the input is valid, otherwise goes to invalid. And since we want to transition between all the states, we want to copy-paste this, unfortunately, to all the states. And this is going to be an abstract declarative way of telling a JSON object that I want this input to behave in this way. And let's get rid of all the boilerplate create React apps offers. Goodbye. And put the input here. And let's say that we need an unchange. There is a delay. And OK, so now we use the machine factory we had from XState. Oh, come on. We pass it the states that we have. I regret not using TypeScript. We feed the machine factory with the state, which is just a JSON object. And then this will give us an object, which is called a statechart. And it has some convenient methods. And how we can connect it to the React view is using useMachineHook coming from XState React binding. And we give it the statecharts. And what it gives you is the current state and a function to be able to send an event so that you make possible transitions. So what you want is that when the input changes, you actually don't want to do anything. Let's just give it a type text, just to make sure that it works by default. And let's give it a placeholder. Enter here. Pretty cool. So you also want to be able to track the value by adding a context here, so that we want to make it a controlled input. We can say there is a value. First of all, it's empty. And you want to pass an actions here to say, update the value for me when I'm transitioning. And you need to be able to add it everywhere, because you're carrying the logic everywhere. And you can perform this action when you're transitioning between different states. And the same for the third one. We're going to get to the refactoring very soon. This is not how you do it in 2019. All right. So as you can see, this is just a bunch of string. Where does the implementation go? Of course. So you keep that abstract because you want to be able to port that JSON, because that's the modeling for the logic. But then you have to pass it the implementation here. So you can pass the config by saying that I have a bunch of guards, that one of them is empty. So all the entities in XState are modeled in a way that they receive the current context and the incoming event, so that you can reason based on them. That's the only thing you need to reasoning. And the is empty when the input arrives. You can say that the data that arrives as the input, it has a length, and that's 0. That's where we say the input is empty. And we do the same thing for saying that if the input is valid or not. And I already wrote a naive validation regex here. I can just import that. Where are you, my validation? OK, here. Just go on. It feels like I'm coding at home. That's how bad I code. Man. Is it validate or something? I can't really see here. And are you is valid? Is email valid? Yeah, sure. OK. What? Cool. The prettier doesn't prettify because I have a problem here. So is email valid? And you give it the data again. Cool. And you have an action to perform, and that's where you pull up something called assign, which is a built-in updater of the context from X state. Basically, just updates this. It's like same as set state. But it gives you an updater instead of mutating the state on the fly. You can pass it an object and say that I have a value that, again, gets context and the event, and you can say that this is here. All right, so the only thing you need to do is that when the input changes, send event. Type, and there is a data, which is the value of the email. Pretty cool. There is an error again. Yeah, I got it. No need to point by hand. I'm kidding. All right, so all right, it works. So what if the input is invalid? We want to show something here. So we can say that if the state, it comes with a pattern matching method for utility. It basically is a strict equality. So it can say that if it's invalid, then we can show something here. Let's give it a class name. I tried my hard to add some styles. And it is invalid. Cool. What happened? Of course, because we're not updating value. Come on, tell me. And we can say, since we keep it in context, we give it context value. And it doesn't update. Does anyone see the problem? What was that? Oh, actions, sorry. Again, TypeScript problem. No, actually, the update doesn't happen. And these types should be target, and target, and target. This happens when you copy-paste. And actions, again and again and again. I'm concerned if we're going to run out of time because I have some cool live coding after this. It's quite hard to live code on the stage, people. Yeah, but it doesn't update because we're not signing something here. Am I missing something again? Actions again. OK, cool. So state.context.value, e.target.value, say type, state.match is invalid. What was that? I don't really hear that, sorry. I have, actually, don't I? Oh, yeah, of course, sorry. Yeah, cool. It's surprising that it doesn't give me any warning for that. All right, cool. Ah, nice. All right. So HolyJS at moscow.com, which is valid. Cool. And otherwise, it's empty. Very cool. OK, so what we can do right now is that to see the visualization for this, we can just copy-paste this state. I heard that. All right. So explicit comes with a built-in visualizer. You can there is the machine factory available there. You can just paste your JSON, and you can see it in action here. Pretty cool. But the problem here is that everything is duplicated around the way. So what you can do is that use a statecharts structure in the states and refactor it in a way that you could just have simpler logic. And for that, instead of having empty states, invalid and valid state, you can say that either the input is updating or it's waiting for the next value. If it's updating, if it's waiting, then you receive type, and you go to updating to take care of updating the context. And the only states you have here are either empty, invalid, or valid. Cool. So when you're in updating now, you just get this one. The same thing, the same transitions. You can say that on entry, when you enter this updating state, update the value. And immediately after updating, go to either one of those. But now, since these empty, valid, and invalid are not in updating, you have to tell it to go to waiting.empty. That's how the state resolution heuristic works in XState. And you have to have an initial state in waiting, which says it's empty. I know that syntax error. Wait for it. And you can say that it goes to empty by default. Now, since you changed, remodeled, you have to also change the initial states here along the way. And line 50, there is a syntax error. And here. And of course, now you can just get rid of all these empty, invalid, and valid states. And of course, here now, since you moved all the actions to updating, it's already in the context instead of being in the incoming event. So what you can do is to refactor this to reason based on the context value. OK, cool. This should be invalid. OK, this live coding is not going well. So what I can do is to show you how the solution looks like if you get rid of this. So what you can do is that you can refactor it in a way that have waiting and updating, and it's still keeping the context. You have updating, as we see. We go to entry. We update the value, and immediately going to either empty, valid, or invalid on waiting. And when you're in waiting, we listen to type, and we go to updating because we abstracted that away. And since we are in, we have to provide child states in waiting and saying that it's either empty, invalid, or valid. But later on, you might want to do something that the business requirements change, and you want to add availability checking. You want to reuse this input in sign-up form. Now you have to do what Google does. You have to check whether the input is available or not. So what you can do is that instead of adding some conditionals and guards, you can just go on and say that when the input is valid, I go on and add checking the state, available and not available. And what I do is that I go to checking immediately, and invoke a promise-based service that is basically returning a promise telling me that the email is available or not. This is how easy it is to refactor later on when you want to add new features. And you probably don't want to immediately go to checking. and like invoke this service. So you can also go on and add debouncing. Time-based enhancements like debouncing and throttling are also completely abstracted and declarative in state charts. And you can just go on and say that there is a debounce delay, which you can just pass along to context again as a string to make it serializable. And you can say that after the delay, go to checking. This is the debouncing. So we wait for a certain amount of time when the user stops typing, and then we start checking for availability. And after that, we want to go on and cancel these requests. What if you're loading that sign-up form in a modal, and then you want, when the user closes that modal, you want to cancel this request. You don't want to swallow all the resources of the user. So what you can do is that statecharts give you the notion of entry and exit action. So adding cancellation is as easy as initializing a controller, passing the signal, saving it in context, passing it to fetch, and when you're getting out of this valid, just tell it to abort it. These two lines will add all the things you want for canceling the request. I really wanted to live code this, but apparently things don't go well all the time. Sorry for that. Another thing that you can model using the statecharts is that not only you can go with the static things, you can also go on and model interactions. For example, a dragging box, something that you could drag inside a container. What if you have a lot of interactions that is relying on a lot of event listeners? What happens there is that you can say that the box is released when you don't do anything with the box. You can start from there too. And you can say when you grab it, it's where you press the mouse button. You grab it, that's where you have to prepare it and save all the points you need from the event, and then prepare it for moving. So you can say it changes the state to grabbed, and then when you start moving, that's where you keep it around. Then you change the state to dragging, and whenever you keep receiving moving, which is when you're like dragging the box around, you just stay in dragging and just update and move the box. And whenever you release the mouse button, the event that will be sent to the state chart is released, and it will basically get back to release. And that's how as easy as it is for modeling an interaction like a dragging box in state charts. And for that, you probably need data like shift and shift X and Y, which is like the pointer positions of the mouse inside the box to be able to perfectly and properly move it, and the page X and Y and X offsets from the container. And the only thing and connection you need with all the event handlers is that basically on mouse down, you send grab, on mouse move, you send move, and on mouse up, you send release. The rest is just abstracted inside the JSON for the state chart. And when I say the rest, it's not something complex. It's just getting those shift data, save it in context, getting those page, save it in context, and basically just change the top and left properties of the styles of the box. That's it. So basically with the state charts, the way that you can connect it is that you get all the events from DOM, you proxy them to the events that needs to be consumed in the state chart, and the state chart will take care of transitioning to different states. And based on that state, React or other frameworks I use will re-render and update the position. One other thing before going to the next scene is that I wanted to be able to compare the old implementation and the new implementation. So the new logic that you're trying to use is the JSON structure on the right side, and the old one, which I copy-pasted from JavaScript.info, is on the left side. For me, personally, understanding the right side is quite easy. I can see that there is a bunch of states that we transition between. That's quite declarative. But on the left side, it's a mingled 30 lines of code into each other that is trying to deal with 3 different event handlers that I don't even know how they work. But there are also additional benefits. One thing that is pretty cool with the state chart is that you can read the logic written in the state chart like English. You can say that the box is released at first. You can just pass it to the voiceover on Mac and let the narrator just read it for you. And you can say that when it's released, it can be grabbed. And as soon as it's grabbed, remember the points. And then we can say that when it's grabbed, it can move. And as soon as it's moving, we update the box. And then when it's moving, it can be released. And when we release it, we keep moving it until, and then when we release it, we keep it on the place, and we're done with it. So basically, there are a bunch of strings you can read from top to bottom, and the relation is quite predictable. Another thing is that state charts, the same way that XState gives you a built-in visualizer, they visualize the logic. And basically, with a bit of graph theory and graph algorithms, you can be able to generate the directed graph or the dependency between different states behind the scenes, and this graph can be used to highlight all the possible paths that the user can take from the state A to B in your application and be able to visualize it. For instance, if you're writing Amazon, the e-commerce website, there are multiple ways for the user to get from the product list, which is the home page, to the success payment page. There are many ways for the user to get from here to there. So to be able to visualize all those paths for yourself or the QA team is what statecharts gives you. And these paths can be used by QA. If there is a dead end, they can easily detect it in the visualization and then try to replicate it instead of just randomly going on and dispatching a couple of smoke tests. It's also very good for cross-competence teams. Imagine that you're working in a team that has different types of developers working with different technologies. I'm a web developer, you're an iOS developer, another one is an Android developer. You have salespeople, product owners, CEO, different types of stakeholders. And you want all to talk about a certain business constraint. Without getting into the implementation detail, a very perfect way to communicate all these logics is writing the state chart, or even not writing it, just giving them the visualization. An image is worth 1,000 words. It's perfect for onboarding too. We're not working on evergreen projects. We might leave the project, and some other people might get to deal with the legacy code we produced. So if they want to, instead of reading a bunch of text in the documentation, just put some visualization of the logic you implemented and be done with it. It's quite easy to understand rather than the text. And this is a live PR that hasn't been closed on Gatsby, from one of the members of XS8 team, and they basically wanted to update something. They update the versions of XS8 used inside Gatsby, and yes, Gatsby is using XS8. And they wanted to open this PR, but somehow they wanted to fix something else along the way too. So an easy way for them to be able to communicate this change is to just dogfood this visualization, use it, put it and embed it in the PR description, and give it to people so that everyone can read it and understand it. This is something you can use from next Monday. Please use it. Also, a very great way, as we talked about, is that since they decouple and everything is abstract and declarative, you can just basically serialize and deserialize this, put it to some other platforms. So as a recap, we learned how adding a new modeling layer can give us multiple benefits and avoid a lot of problems. We have seen that if you use a good, proper modeling, you can level, at the best time, level the complexity of your problem to the complexity of the solution. There are implicit and explicit ways to think about a state, and states can be finite or infinite. And you can use a state chart for practically modeling complex graphical user interfaces, which makes impossible state impossible. And also, they avoid mutual exclusivity problems. The only thing I want you to take away from this talk is not to learn how to work with XS8 or state charts or even use them in JavaScript or React or Vue or whatever. I only want you to think about the states. That will take you so far from there. Just think about the states explicitly. It's more of a shift of mindset. The way you changed your mindset from imperative code to declarative code, you're going to have to take the same thing from thinking about the states implicitly to explicitly. And when you see it, you can't really unsee it after that. If you want to check out more resources, there is a great resource called The World of State Charts at statecharts.github.io. You can check the official docs of XS8 and also the alternative robot. And do not let your software bully you. Thank you very much.